All right, so here's part 3 of our discrete distributions lab. So we've covered the Bernoulli, the success-fail situation. The geometric, this is repeated Bernoulli trials, and we're wondering what's the probability of having your first success on the nth trial. So we can have a distribution that goes out as far as n as you want, but it's still discrete because there's still whole number outcomes. And now we have the binomial distribution. This is the one that's mathematically the most complex, so we're going to use a function to calculate it. So what is a binomial distribution? It describes the probability of getting a certain number of successes in a fixed number of Bernoulli trials. So if I have 10 people in a room and I consider that a sample, what's the probability that exactly half of them is female, exactly half of them is male, or 2 of them are male? That would be considered a binomial distribution. So here's the probability of finding it given n trials. This is your size of your group. K successes is the people meeting your condition that you're interested in, and P is the probability of that condition. So it's a mess. Uses factorials, and who even knows what that is. So in R, we can simply do that calculation using dbinom, where we specify K, N, and P. So let's look at an example. The example of meeting our deductible, we had a probability being 0.3, 30%. And suppose we were a small company and we had 8 people in our company, and we wanted to know what's the probability that exactly 3 of them meet their deductible. So we'll call success meeting the deductible. So that means we can make P 0.3. That's the probability of success. We have N people. That's the size of the group that we're interested in, 8. We want to know what the size of having exactly 3 successes is 3. And if we put those in right, dbinom takes in X first, or K, I should say, N it puts in for size, and P is for probability. This gives us the probability of having exactly 3 people out of 8 meeting their deductible. And so some of the theory is similar to the way we found the binomial distribution. It just gets more complicated because the order in which we're selecting people changes. So that's why the formula has a similar piece here, P to the K, 1 minus P, but the ordering makes it more complicated. So let's do another example. Suppose you have 5 people out of 8 that are not meeting their deductible. Okay, not meeting the deductible would be 0.7 because we're changing what our success is. Again, if we have 8 people and we're looking at 5 people not meeting the deductible, look at what that is. So consider we got the same answer in both these problems. So what's going on here? Notice if I have 8 people, 3 out of 8 meeting their deductible is exactly the same as 5 out of 8 not meeting the deductible. So this is nice. We can model the situation in any way you want, call success whatever you want to, but as long as we're consistent, it will give us a correct probability. So if we want to consider the whole distribution of 8 people, how many out of 8 meet their deductible? You can plot it, and you can see the most likely is 2. 0, it's not very likely. 1, more likely. 2 is the most likely. 3, 4, and so it has that nice curve. And we'll look at later what happens when we get bigger and bigger n to that curve. It's kind of interesting. So your next problem says, what's the most likely number of people we're going to meet in this situation? It looks like there's going to be, most likely is 2. It's the highest probability if we plot them all. And so what's the probability of getting exactly 2 out of 8? Well, to make it kind of easy on me, I'm just going to copy this code. This is really one way to do a lot of statistics, is know what code you're using and make sure you put in the right numbers. So if I want to know exactly 2 out of 8 meet the deductible, I'm going to say 0.3 is meeting the deductible. That's my success. Got 8 people. We want to know what's the situation when 2 meet it. 29%. Yeah, it was slightly more than 3. 29.6%. So you can answer 14. What's the probability that all 8 out of 8 don't meet the deductible? And then Okay, what if we sampled 20 people? What would be the most likely? What would we expect? So 2 ways to answer it. You could modify this distribution to make it for 20 people. Say n is 20. Probability of success is 0.3. So meeting the deductible is the same as exceeding. And we're just going to change this to n equals 20. So it looks like, according to this distribution, 6 is going to be the most likely. The other way you could do it is you could say, well, hey, I got 20 people, and the chance of meeting your deductible is 0.3. That also gives us 6. If we were just to average it out, law of large numbers says I would just multiply the chance of the success, and that's how many people in a group would meet it. So the tricky thing with this distribution is finding out when it applies. So this can help us. There's 4 conditions we have to look at, and some of them can be kind of related, but we need a fixed number of trials. We need trials that either a success or a failure. We want the probability of success to be the same for each trial, and each trial has to be independent, has to not affect the other trials. So randomly sampling satisfies these last 2 if I'm sampling a random group. So what if I want to know, okay, the probability of a smoker developing cancer is also about 0.3. Suppose you have 4 friends, all of which you smoke. Do we satisfy these 4 conditions here? Let's see. Are the number of trials fixed? You can say yes, because there's 4 friends. N equals 4. Is each trial an outcome, success or failure? I guess developing lung cancer. Lung cancer, either you do or you don't. Satisfies this. Probably success is the same. If we're considering this as a random sample from a group, yeah. I mean, if we're considering these people just from the population, we can assume it's the same probability. But let's see, are they independent? Well, not really, because the friends might have other habits that are linked, not just smoking. So the fact they smoke means, yeah, they're going to have a 30% chance of getting cancer, but they also might have other habits, and maybe they drink together. Maybe something else will cause them to get cancer. So this is not satisfied, and that's sometimes difficult in an experiment to satisfy. So what we then do is we assume, hey, let's just say it does, even though we admit one of these conditions is kind of iffy, and then we can proceed with our analysis. So using our same distribution, you can answer the rest of these questions. And did we answer? I want to help you with part D. Well, it should say C here. Excuse me. I'm going to copy my code. And if you finish A and B, you can unpause it and go to C, but do pause it to try to figure out those before you proceed to this one. So here we're looking at the probability that 1 or more will develop lung cancer. So that would be 1, 2, 3, 4, 5, 6, 7, 8 people. And these will be independent events. So we have to find out the probability of each of these 8 cases and add them up. It's going to be a lot of numbers. But if you wanted to be fancy, we're looking at successes being 1, 2, up to 8. So if I run this bit of code, look what K is. It says K is 1, 2, 3, 4, 5, 6, 7, 8. So this is called a vector. I can have multiple numbers stored in there. And this middle symbol is called a colon. I can calculate this all at once. And I'll fix this to getting cancer. So here's kind of a nice thing that I calculate all these numbers all at once. And now I just want to add them up. So if I make this thing just X, some place to store my numbers, then I can say sum X. And it'll find me the sum of all those probabilities, and I can find it all in one go. So adding up those numbers gives me a 94% chance of getting lung cancer. Okay, so that's some tips on these combined probabilities. If we're looking at like 3 or more, or less than 2, you'll have to consider what outcomes you're looking at, and adding them up will give you the joint probability. Okay, and then there's an extra credit. If you want, delete that line and you can work on the bonus. Okay. Good work. Keep up the good work. We'll see you in class. Take care.